Hello everybody, I am Sandeep Dasgupta and I am from University of Illinois at Urbana-Champaign, working with Professor Vikram Adve. The topic of my presentation is scalable validation of binary lifters, and I would like to take this opportunity to thank my awesome colleagues Sushant Dinesh, Deepan Venkatesh, Professor Vikram Adve, and Professor Christopher Fletcher. I'll begin my presentation with the fact that binary analysis is important. The ability to directly reason about the binary code allows us to prove or disprove properties about the code which is actually going to get executed. This is as opposed to source-level analysis, which may not be desirable in various scenarios. For example, when the source code is not available, or there are scenarios when it is not desirable to trust the compiler. Binary analysis is generally performed by existing decompilation or reverse engineering platforms, which are broadly implemented using a three-step process. First, the binary code is disassembled to assembly code. This translation exposes various high-level properties like instructions, control flow graphs, function boundaries. Next, the assembly code is transformed into a high-level IR using a tool known as Lifter. This tool allows the decompilation framework to handle the complexity and diversity of multiple ISs. Finally, various analysis and transformations are performed on the lifted IR. This step is meant to serve one or more of the following goals, like recovery of types, variables, and functional prototypes, and so on and so forth. In this presentation, we will be focusing on the tool Lifter. Developing a lifter, especially for complex modern ISs, is challenging and error-prone, mainly because manually encoding the effects of a vast number of instructions is hard. This is made even harder because the informal specifications provided by hardware manufacturers run into thousands of pages and are often ambiguous, buggy, or include divergence in the behavior of variates. For example, here is the semantics of move SD instruction with its register and memory variant. And as we can see that the semantics of the register variant is different from that of the memory variant. Binary lifting is considered as one of the central steps in many binary analysis and instrumentation systems. In this diagram, each circle represents a particular IR being used by one or more binary analysis or instrumentation systems. For example, LLVM IR is used by Maxima, FCD, and several others. BIL is used by BAP, and so on and so forth. The key point is faithful binary translation strengthens trust in binary analysis results. Our main goal is to develop formal and informal techniques to achieve high confidence in the correctness of binary lifting from a complex machine ISA to a rich IR by leveraging the semantics of the languages involved. The prior work falls short in at least one or more of the following criteria. Either they require random testing, which leads to incomplete coverage, or they use symbolic execution and are restricted to single instruction or basic block level validation that do not scale to full program validation. On the contrary, our main goal is to support full program validation. Some of them require instrumentation of the lifter framework to emit additional information required to prove correctness. We deliberately moved away from any such instrumentation-based approaches so as to avoid the overhead of maintaining instrumentation patches whenever the lifter got updated. Our current work focuses on validating the translation from x86-64 programs to LLVM IR using Maxima, which is a matured, actively maintained, and open source lifter. Please note that the underlying techniques of our approach are generic enough to be applied to other lifters in a straightforward way with some engineering effort. Our approach is inspired by the observation that most binary lifters are designed to perform simple instruction-by-instruction lifting followed by standard IR optimizations to achieve simpler IR code. Such an observation motivates us to foresee the possibility that formal translation validation of single machine instructions can be used as a building block for scalable full program validation. Let me lay out our approach, which has two key phases. The phase 1 is single instruction translation validation, which is the translation validation of the lifting of individual instructions in isolation. This leverages our prior work on formalizing x86-64 semantics, which is published in PLDI last year. In phase 2, we devised a scalable approach for full program validation built on top of phase 1. Phase 2 is much cheaper than symbolic execution based equivalence checking. Our work has three major contributions towards developing a scalable technique for validating lifters. First, we developed a single instruction translation validation framework for an architecture as extensive as x86-64. Next, our single instruction validation framework revealed bugs in a mature lifter like Maxima. Finally, we devised a novel full program validation strategy, avoiding heavyweight symbolic execution. In the next few slides, we will walk through the first phase of our approach using a short animation. Let me reiterate our goal. On the left, we have a binary program P, which is lifted by a lifter, which is Maxima in our case, to a lifted IR program T on the right. Our goal is to validate the translation from P to T. Single instruction translation validation is about validating the lifting of individual instructions of a program in isolation. We start with the binary program P, isolate the constituent instructions, which are then lifted individually by the lifter D. The binary instruction and the corresponding lifted IR sequence are then fed to a single instruction translation validation framework, which could have two outputs. Either it will say that the translation is validated, in which case we cache the pair of binary instruction and the lifted IR in a stored cache. Similar decisions could be made for other instructions. Or the framework will say that the validation failed, in which case we found a bug to be reported. Let's have a peek inside of this single instruction translation validation framework, which takes as input the binary instruction I and the lifted IR sequence S. First, the binary instruction is symbolically executed using x86-64 semantics, which we developed as one of our prior work. The output of the symbolic execution is a symbolic summary. Similarly, the lifted IR sequence is symbolically executed using LLVM semantics in order to generate the corresponding summary. The two summaries are then fed to a verification condition generator. The generator generates satisfiability checks as shown here to ensure that the two summaries are equivalent. The checks are then fed to an SMT solver, which say that the checks is satisfiable, which means that the translation is incorrect to be reported as a bug in the lifter's translation. Or it will say that the check is not satisfiable, in which case the summaries are equivalent, implying that the lifted IR sequence is the correct translation of the binary instruction. Please note that the symbolic execution engines are auto-generated using K-framework. Also, the symbolic executions are not performance heavy because, as per the x86-64 ISA specification, only a few instructions exhibit loops in their semantics. A key point to note here is that the single instruction translation validation cost can be amortized by the fact that many instructions are reused within or across programs. As shown previously, that we are caching the validated pair of binary instruction and its corresponding LLVM IR. Such validation results can be reused, amortizing the validation cost. The single instruction translation validation framework found 29 solver failures, which were all confirmed as bugs by the Maxima developers. Some of them are fixed as well. Let me go over a few of those reported bugs. On the left, we have the correct version of exchange at operation as suggested by the Intel manual. In this particular instance, RAX is the source operand and RBX is the destination operand. The two operands are added in step 1. In step 2, the source register is updated with the destination operand. And finally, in step 3, the destination register is updated with the added value. On the right hand side, we have the Maxima's implementation of the same instruction when the operands are the same registers. And we can see that the steps 2 and 3 in the left hand side are reversed in this implementation. As a result, the value of the destination register RBX at the end of the instruction is the input value of RBX, whereas using the correct implementation on the left, the destination value should be twice the value of input RBX. This bug is related to compare exchange instruction, where as per the correct semantics on the left, EAX need to be compared with temp, whereas in the buggy implementation on the right, 0 concatenated EAX is compared, which is indeed a bug. Let me lay out the phase 2 of our approach about full program level validation. At the end of single instruction validation, we have the validated IR sequence for all the constituent instructions of binary program P. The intuition behind our program level validation strategy is to somehow leverage these validation results. Specifically, Our strategy is to propose an alternate reference program T-bar generated by carefully stitching the validated lifted IR sequences corresponding to the constituent instructions of the original binary program P. This is achieved using a tool called Compositional Lifter, and the idea is to compare its output, which is T-bar, with the original lifted IR T for semantic equivalence. Next, T and T-bar are subjected to semantic preserving transformations so as to reduce them to a common form, one function at a time. That way, the semantic equivalence between T and T-bar can be reduced to a much cheaper graph isomorphism check realized using a tool called Matcher. The next few slides will explain this strategy using some animation. From my prior explanation of single instruction validation phase, we are aware of the store cache which is populated by that phase with the validated pair of binary instruction and the corresponding lifted IR sequence. Assume that the store cache as shown here is just an instance of it. As before, we have the binary program P, and our goal is to come up with a reference IR program T bar, which we can later match for equivalence with the original lifted IR program T. The idea behind compositional lifting is to go over the individual instructions of P, like this first instruction here, and check if the instruction is in the store cache. If yes, we stitch the corresponding lifted IR sequence to the reference program with some glue code. The glue code is specific to a particular lifter and is the most important thing that needs to be changed if we want to extend our approach to other lifters. We'll do the same thing for other instructions as well. So now we have the reference program T bar. Also, we have the original lifted program T. We feed the candidate pair of functions f and f prime from these programs to a transformer, which is essentially a set of LLVM optimization passes used for transforming the two functions to a common form, fn and f prime n. At this point, we compute the data dependence graphs from the transformed version of the functions. A node of the graph represents a LLVM instruction, and an edge represents the SSA diffuse or memory dependence relation. The graphs are then matched for graph isomorphism. A successful match implies that the function from T and T bar are semantically equivalent, meaning that the original lifted function is the correct implementation of the binary function. An unsuccessful match leads to a potential bug in the lifter's translation. The reason that we can have false alarms is because it is quite possible that the LLVM optimization passes are not effective to reduce the otherwise semantically equivalent functions to isomorphic graphs. We note that our argument about isomorphism of data dependence graph implying semantic equivalence of the functions f and f bar is based on the pioneering work by Horowitz et al., which proved that if the program dependence graph of the two programs are isomorphic, then the programs are semantically equivalent. Our dependence graph representations, which we check for isomorphism, only include the data dependence, not the control dependencies. Note, however, that the close structural similarity between the functions f and f bar ensures the required equivalence for control flow as well. This is shown in our paper. The transformer is for pruning off the syntactic differences between T and T bar, except for the names of virtual registers and the order of non-dependent instructions. The transformer uses a list of LLVM optimization passes, one for each function pair. The pass list is derived using pass sequence autotuning. Note that the optimization passes are not formally verified. For autotuning, we use the OpenTuner framework, which uses a search space including 17 LLVM optimization passes, all discovered manually. The objective function of the autotuner is to maximize the number of matching nodes of the candidate data dependence graphs. Our program-level validation strategy is evaluated on 2,348 LLVM single-source benchmark functions. Following are the runtime of the different components of the pipeline. For example, the compositional lifting takes about 0.05 seconds to 6 seconds, autotuning takes about 10 seconds to 20 minutes, and the matcher takes 0.06 seconds to 120 seconds. With our program-level validation strategy, we proved the correctness of 2,254 out of 2,344 translations with a success rate of 96%. The LOC of the lifted IR ranges from 86 to 32,105. The manual inspection shows that the remaining 4% are false alarms. In summary, The validation of lifters without instrumentation or heavyweight equivalence checking is feasible, and formal translation validation of single machine instructions can be used as a building block for scalable full program validation. With that, I will conclude my presentation and we are open to questions.